All right, so we're going to go back and do some more Venn diagrams. We're going to take a look at a problem that we previously did without showing a Venn diagram on it. We did it by complements, and this is the antibiotic problem. So two antibiotics are available as treatment for common ear infection for children. Antibiotic A is known to effectively cure the infection 60% of the time. Please note that means that it fails 40% of the time. That's not a commentary, that's just a fact. Treatment with antibiotic A costs $50. Antibiotic B is known to effectively cure the infection 90% of the time, which means it has a 10% failure rate. So fails 10% of the time. Treatment with antibiotic B costs more at $80. The antibiotics work independently. This is a very, very important word because remember, if events are independent, we can multiply them, and that might be very important to us later. Both antibiotics can be safely administered to children. A health insurance company intends to recommend one of the following plans. This health insurance company is really important because this gives us context. This is who's making the recommendation. This isn't your mother, this isn't a father, this isn't the drug company, this is the health insurance company. So think about what their motivation might be when you're answering this question. Plan 1, treat with antibiotic A first. If it's not effective, then treat with antibiotic B. Plan 2, if B first. If it doesn't work, then go to A. So if a doctor treats with a child with an ear infection using plan 1, what's the probability that it'll be cured? Then they ask the same thing if they use plan 2. All right, so I'm going to look at this from a Venn diagram standpoint, and I'm not going to show all my work for all of this because we've previously done this. We have a previous video on this, but they told us these things were independent, and we happen to have two drugs, A and B. And so I'm going to start off by just drawing a little Venn. It looks like this. I'm going to make a big area for the intersection just because it makes my life easier when I have a big area for the intersection, regardless whether it's not. What a beautiful circle that one is. So we have drug A and we have drug B here. Now, the intersection, that's the overlap. And remember, they told us they were independent. So the probability of A intersect B equals the probability of A times the probability of B. Now remember, I can only multiply these probabilities if they are independent. And they did tell us they're independent. And so this right here, this intersection is my overlap. I'm just going to put a little intersection symbol right here because that's my overlap. Well, we know the probability of A success is 0.60. And then we know the probability of B success is 0.90. And when we multiply them, we end up getting 0.54. So this is my overlap. All right, so this is my overlap of 0.54. All right. Now, when I look at plan A, not plan A, drug A has a 60% success rate. So what's in this circle needs to sum up to 60%. So 0.60 minus 0.54 means we have 0.06. So 6% of the time, drug A works when drug B doesn't. All right, so 6% of the time, drug A works when drug B doesn't, and 0.06 plus 0.54 gives me the 0.60. So I'm going to go ahead and highlight this section. I'm just going to use a blue highlighter. All right, now we have drug A. Well, drug B works 90% of the time. So the time when it works by itself is 0.9 minus 0.54, which means 36% of the time drug B works by itself. Drug B works when drug A doesn't. 36% of the time, drug B works when drug A doesn't. And I'm going to go ahead and highlight this. I'll just use a little pink here. All right. But if I sum these up, they do not sum up to one whole. So that means there's a part of the time when neither work. So if I subtract 1 minus 0.06 plus 0.54 plus 0.36, I end up finding that there's a 4% of the time when they don't work. Now, if I sum these up together, 0.36, 0.54, and 0.06, I find out that they work 96% of the time. All right, they will end up working 96% of the time. And I want to go on to express this in terms of the addition principle. The general addition principle can always be used. The general addition principle was a probability of A union B equals the probability of A plus the probability of B minus the probability of A and B minus the intersection. All right, but they told us they were independent, and since they are independent, I can plug that in. So now my probability looks like this. The probability of A union B equals the probability of A plus the probability of B minus the probability of A times the probability of B. Once again, I can only make this substitution because they were independent. If they were independent, I couldn't say that. Because they're independent, I can multiply them and know that A times B equals the intersection. Well, the probability of A success happens to be 0.60. The probability of B success is 0.90. Now, if I look at that, that's 0.6 plus 0.9, that's 1.5. You can't have a 1.5 probability. So the good thing is I do get to subtract. So probability of 0.6 times 0.9. This ends up being 1.5 minus 0.54. And we end up getting a 0.96. We end up getting a Q rate of 0.96 for A union B. If I were to swap the order, I would get the same thing. I'm not going to take the time to show this. But the question is that I often get is, why did we subtract the 0.54? And that's not supposed to be 1. That's just a 0.54. Why did I subtract the 0.54? And the reason I subtracted the 0.54 is because it got counted twice. It was included with drug A. It's in the 60% ring. That's why it's shaded with the blue. It's also included with drug B, which is in the 90% ring, which is why it's shaded pink. So it got counted twice. And because it was counted twice, I have to subtract it out. We can only count it once. So I could add straight across this plus this plus this, and I'll get 0.96. But when I add just a 0.6 and a 0.9, I have 1.5, which doesn't make sense from a probability standpoint. But if I subtract out the overlap, they counted twice. I'm going to say it once more. I'll try one more time. So 0.6, this first 0.6 included that 0.54. That's good. But the 0.9 also included it. And since each one included, it was counted twice, therefore I must subtract it out. Now, had I done the same problem, so this was working at it from a plan 1 perspective. Had I worked at it from a plan 2 perspective, it would have been the probability of B union A equals the probability of B plus the probability of A minus the probability of A and B. So this again just becomes 0.9 plus 0.6 minus the 0.54. So just swapping the order didn't change anything. So plan 1, and this is plan 2. So plan 1 and plan 2 have exactly the same cure rates. But then when we go to look at the cost, well, with plan one, and actually this is true with both of these plans. Both of these plans, you're going to buy one drug, and if it doesn't work, then you're going to have to buy two drugs. So plan one, we buy A, or we might have to buy A and B. If we just buy drug A, it costs $50. If we have to buy A and B, it's the 50 plus 90, so it's $130. So that's what we have to buy. The question is, what do we do about this? Well, this time, it works 60% of the time, which is 0.60. 60% of the time we can get by with just spending $50. But 40% of the time, I have to buy both, which in this case, when I do the math, 60 times the 0.5 plus this ends up being $82. So on average, we expect to spend $82. Once again, no one's paying $82 because you're either paying $50 because you bought drug A and it worked, or you had to buy A and B and you spent $130, or the insurance company spent $130. So the insurance company is never spending $50. They're never spending $82. They're either spending $50 or $130. But because 60% of the time they're spending this, 40% of the time they're spending this, on average or in the long run, they're spending this. They're spending the $82. If we look at plan two, now we're looking at buying drug B. And if that doesn't work, we'll have to buy them both, B and A. Well, drug B costs $80. And B and A, 80 plus 50 is still 130. So if we have to buy both of the drugs, we're still at $130. Well, if we use plan two, 90% of the time, we're only spending $80. And 10% of the time, I'm having to spend $130. When I do my math, I find out that plan two cost $85. The insurance company is never paying $85 for a single plan two. That never happens. They're either spending $80 or $130. 90% of the time they're spending $80, but 10% of the time they're stuck with $130. So on average, or in the long run, they're spending $85. So when we go back to part C, it says based on the results in A and B. So based on the results of A and B, so I need to make sure I include A and B. I can't make it just a decision on cure. I can't make it just a decision on price. I need to make it on both. What would the insurance company, what would you plan for what would you recommend for the insurance company? All right, so first off, let's look at part A. Part A, we have the same cure rates at 96%. So I'm just going to say that. The cure rates are the same. So there's no difference, in which case I'm not too worried about the cure rate, but I just needed to make sure that they understood that I considered it. They're the same, so they don't really impact it. So I'm going to be making this on cost basis, and I'm the insurance company, so insurance is going to want to minimize the cost. So recommend plan one. To minimize costs on average, we expect to save $3 an infection using Plan 1. Okay. All right. Thank you. And we'll stop the recording.